Okay, so good day everyone. I'm Nabili Mampao and I'm with Miss Warda Asum and we are here to discuss refrigeration. So refrigeration is a very common process to us. Why? Because refrigeration can be observed in our very own homes. But if you ask people how does refrigeration works, they might not know the answer to that. So let's discuss refrigeration. First is let's define it. So refrigeration is the process of removing heat from a substance under controlled conditions. So in a refrigerator, heat is virtually pumped from a lower temperature to a higher temperature. That is the technical definition of refrigeration. So refrigeration is a continued extraction of heat from a body or an object. Theoretically, refrigeration is the reverse process of heating. According to the second law of thermodynamics, the process can only be performed with the aid of some external work. That means that refrigeration will not take place without the help of an external work. Uh, that external work will be discussed thoroughly later in the video. So now let's move on to the vapor compression system. So vapor compression refrigeration systems are the most used among all refrigeration systems. In a vapor compression refrigeration system, refrigeration is obtained as the refrigerant evaporates at low temperatures. The input to the system is in the form of mechanical energy required to run the compressor. Hence, these systems are also called as mechanical refrigeration systems. Essentially, a vapor compression refrigeration system is a system that uses liquid refrigerant in a closed system, which circulates the refrigerant through four stages, which is alternately compressed and expanded, changing it from liquid to vapor. So as this change happens, heat is either absorbed or expelled by the system, resulting in a change in temperature of the surrounding air that is passing over the unit's components. So nearly all refrigeration systems use this cycle to accomplish cooling. So to understand more, let's look at this figure. So in the name itself, vapor compression cycle, in this process, vapor is compressed to produce refrigeration or a cooling effect. So the four stages that is mentioned is in the evaporator, then to the compressor, then through the condenser, then through the thermostatic expansion valve. So this will be discussed more on the refrigeration cycle. So let's move on to the refrigeration components. So first one is the compressor. So compressor is the heart of refrigeration cycle. That means that without the compressor, refrigeration will not take place. So these components are the external factors that are mentioned that is mentioned earlier. So the compressor is responsible for moving the refrigerant between the evaporator and the condenser coils, ensuring that the refrigerant changes to gas or liquid as needed. So compression of refrigerant to the suitable pressure ensures its proper condensation and circulation throughout the conditioning depends entirely on the capacity of the compressor. So here is a sample that shows the parts of a compressor. So there is a shell, electric motor, suction muffler, the cylinder, and the discharge port. So the inlet where the refrigerant goes through is called the suction line, and After it is compressed, it goes out through the outlet, which is called the discharge line. So there are three types of compressors. So first one is the reciprocating compressors. This is widely known as piston compressors and are mainly used to move air or gas at high pressure to be stored and used for different purposes. So the main elements of the compressors are one or more cylinders and pistons which move within them. So the reciprocating compressors are the most widely used compressors in most refrigeration systems. So there are three types of reciprocating compressors. So first one is hermetically sealed. Next one is semi-hermetically sealed in the open type. So in hermetically sealed compressors, the compressor and the motor are enclosed and the welded steel casing and the two are connected by a common shaft. So this makes the whole compressor and the motor a single compact and portable unit that can be handled easily. So next one is the semi-hermetically sealed compressor. So it is designed to address some of the major shortcomings of the hermetic compressor. So semi-hermetic compressors use a cast iron casing for the essential part. So the motor and compressor are still housed together, but they can be accessed as needed. This enables maintenance checks and repair of replacement of parts and as they degrade rather than a total failure of the system. So that is the difference of semi and hermetically sealed and a hermetically sealed compressor. While the last one is the open type compressor. It is an open compressor wherein the motor and the compressor are mounted separately. So the purpose of this is so that compressor components are easy to access for maintenance and the cost of the shell can be avoided. The second type of compressors is the rotary compressors. So rotary compressors are a subset of positive displacement machines. Rotary compressors have a number of features in common even though there are differences in construction. Unlike reciprocating compressors, rotary compressors do not use valves to move the gas through the machine. Rotary compressors' physical design varies widely. Both single and multiple rotor constructions are used. So the design of rotor is the main item that distinguishes the different types of rotary compressors. So when compared to a reciprocating compressor, uh, rotary compressors are lighter in weight and it experiences less vibration and it does not require heavy foundations. Next one is the scroll compressors. This is the last type of compressors. So a scroll compressor has one fixed scroll which remains stationary and another moving or orbiting scroll that rotates through the use of swing link. So the scroll compressor is also known as a scroll pump or a scroll vacuum pump. The advantage of using a scroll compressor is that it has fewer moving parts and less torque variation compared to the reciprocating compressor and the rotary compressor. So this advantage is translated to a smooth and quiet operation. The scroll compressor is also I've already said that. Now for the second component of refrigeration, let's discuss condenser. So the function of the condenser in a refrigeration system is to transfer heat from the refrigerant to another medium, such as air or water. So by rejecting heat, the gaseous refrigerant condenses to liquid inside the condenser. So the condenser removes thermal energy from the superheated vapor which is discharged by the compressor, turning it into a saturated liquid. After losing all the latent energy, this liquid is said to be subcooled. To further understand the function of condenser, let us see this figure. So, the high pressure superheated vapor from the compressor enters the condenser through the inlet. So since the condenser is very cold, thermal energy is rejected, which then condenses the superheated vapor. So as you can see, there is a fan in the figure, and the purpose of that fan is to make sure that the condenser is always cold. So if you see a fan in your refrigerators, the purpose of that is to make sure that the condenser is always cold, because if it is hot, it can't condense the superheated vapor from the compressor. So upon leaving the outlet of the condenser, the high pressure superheated vapor turns into a high pressure liquid refrigerant. This liquid refrigerant will go through the outlet and into the expansion valve. Now let's discuss the third component of refrigeration, which is expansion valve. So the expansion metering device is connected between the condenser and the evaporator. It makes the break point between the high and low pressure sides of the system. The expansion valve removes pressure from the liquid refrigerant to allow expansion or change of state from a liquid to a vapor in the evaporator. The expansion device consists of a restriction or small orifice through which the liquid refrigerant from the condenser is forced to flow. This creates a drop in the pressure of the refrigerant, thereby decreasing its boiling point accordingly. This in turn causes part of the liquid to turn into vapor, and the temperature of the remaining liquid decreases to its high resistance to the flow of refrigerant. The expansion device regulates this flow to the evaporator. So there are two types of expansion valve, which is capillary tube and thermostatic expansion valve. So let us see this figure. So the subcooled liquid from the condenser will now enter this expansion valve. So as the liquid flows through this tubing, it loses pressure. Why? Because the tubing has a small diameter, and as the pressure drops, the boiling point of the liquid drops accordingly. That's why some of the parts of the liquid turns into a vapor. So from the subcooled liquid from the condenser will exit the expansion valve as a mixture of vapor and liquid with low pressure. This is another type of expansion valve, which is a thermostatic expansion valve. Now, let's move on to the fourth component of refrigeration, which is the evaporator. So the evaporator is located within the cooling chamber. It turns the mixture of liquid and gas refrigerant coming out of the expansion device into a low pressure superheated vapor. So in the process, the evaporator removes thermal energy from the cooling chamber. Most of the cooling effect in a refrigeration system happens in the evaporator. So now let's discuss how the evaporator works. So the cold mixture of liquid and gas from the expansion device will now enter the inlet of the evaporator. As the mixture flows through the coils of the evaporator, it absorbs thermal energy that surrounds the evaporator and the coil itself. And as you can see, there is a fan that is in the figure, and the purpose of that is as soon as the mixture absorbs all of the thermal energy, the coil of the evaporator cools. Then the fan will distribute the cool air into the surrounding of the evaporator. Then the mixture of liquid and gas will turn into a superheated vapor, which then will exit the evaporator through a tube and through the compressor. Now, let's discuss the fifth component of refrigeration system, which is the refrigerant. Refrigerant is a cooling agent that absorbs heat and leaves cool air behind when passed through a compressor and evaporator. It fluctuates between a liquid or gas state as it goes through the thermodynamic process. So there are different types of refrigerant. The R12 refrigerant, the R22, R290, R134A, R40A, R4410A, R450A. So some of this has been banned because it is not environmental friendly. There are also other types of refrigerant that is environmentally friendly, like the R290, R450A, R513A, and R600A. So refrigerant has a great effect on global warming. That's why some of the types of refrigerant has been banned by the law. So refrigerant's environmental impacts is measured by the following characteristics. So ozone depletion potential, and the global warming potential.
So let's proceed to the refrigeration cycle. The refrigeration cycle starts at the compressor, and then with the condenser, then with the expansion valve, and then with the evaporator and back to the compressor. The refrigerant flows into the compressor where it is compressed and pressurized. At this point, the refrigerant is in hot gas. The refrigerant is then pushed to the condenser, which turns the vapor into liquid and absorbs some of the heat. The refrigerant then proceeds to the expansion valve where it expands, losing pressure and heat. The refrigerant coming out of the expansion valve is cold and slow due to the loss of pressure. It then enters the evaporator in a liquid state where the exchange of heat takes place, thus cooling the load inside the refrigerator. As the gas cools down the load, it absorbs the heat which turns it into a gas. The gas is then pushed back into the compressor where it can start the cycle again. The refrigeration cycle of a system can be represented by simplification of pressure enthalpy diagram of the refrigerant it uses. Having a brief discussion about enthalpy, the amount of thermal energy per unit of mass of a refrigerant is called enthalpy. Enthalpy can be measured in different units, such as in metric or SI units of kilojoules per kilogram, in US custom units of British thermal units per pound mass. As it flows through the evaporator to refrigerate the space, the refrigerant absorbs thermal energy. Consequently, the enthalpy of the vapor at the outlet of the evaporator is greater than that of the liquid at the inlet of the expansion device. The thermal energy absorbed per unit of mass of the refrigerant is called the refrigerant effect. Refrigerant manufacturers normally provide tables indicating the enthalpy of the refrigerant at various temperature. In the next slide, you can see the example of an enthalpy table for R134A refrigerant at different temperatures. The table shows the equivalent of enthalpy at the different temperature at a given pressure. The figure then shows the pressure enthalpy diagram. Refrigerant manufacturers provide a diagram that shows the enthalpy of their refrigerant as a function of absolute pressure. A simplified version of a pressure enthalpy diagram is shown in this figure. The horizontal axis of a diagram is graduated in enthalpy units, which lies on the x-axis, while the vertical axis is graduated in the absolute pressure units that lies on the y-axis. Two curves on the diagram indicate the changes in state between the saturated vapor, which lies on the right-hand curve, while the saturated liquid lies on the left-hand curve. Between these two curves are horizontal lines of constant temperature, and these lines that you see here are the constant temperature. A point representing A point representing the current refrigerant pressures that is located on horizontal line indicates the refrigerant is a mixture of liquid and vapor. If this point is located on or to the right of the saturated vapor, the refrigerant is superheated. If this point is located on or to the left of the saturated liquid curve, the refrigerant is subcooled. Important characteristics of refrigeration system are the net refrigeration effect, heat of compression, and the coefficient of performance. These properties can be determined graphically by using system's refrigeration cycle, which refers to this figure. The net refrigeration effect or cooling load is the enthalpy removed by evaporation. It is then determined by drawing vertical lines downward from points 2 and 3. As you can see, there is the number 2 and 3 in the figure. The difference on the enthalpy horizontal axis where the lines cross this axis is equal to the NRE. The heat of compression is the enthalpy added to the vapor, mainly by the work done by the compressor. It is determined by drawing by vertical lines downward from points 3 and 4, which is here and there, 4. The difference on the enthalpy horizontal axis where the lines across this axis is equal to the heat of compression. The coefficient of performance is a pure number of indicating the efficiency of the refrigeration cycle. It corresponds to the ratio of the enthalpy removed by evaporation to the enthalpy added to the vapor during the compressing phase. And in the equation, in the next slide, the equation is shown. The coefficient of performance is equal to the net refrigeration effect or cooling load over the heat of compression, which is then equal to refrigeration capacity over work input to compressor. For a refrigeration system operating between a higher temperature of TH and a lower temperature of T sub L, the coefficient of performance is equal to T sub L over T sub H minus T sub L. Note that T sub H and T sub L are absolute temperatures, which is in degrees Kelvin. For refrigeration, coefficient of performance will always be greater than 1, which is typically not less than 2.3 and not greater than 3.5. The higher the coefficient of performance, the better the efficiency of the system. The coefficient of performance of refrigeration systems varies according to the condition under which they operate and the components constituting them. Therefore, it should not be used to compare the performance of two refrigeration systems that operate under differing conditions and or that are not entirely made up of the same components. Domestic and commercial refrigerators may be rated in kilojoules per second or in British thermal unit per hour of cooling. Commercial refrigerators in the US are mostly rated in tons of refrigerations, but elsewhere in kilowatts. For the information of everybody, British thermal unit is a measurement of heat energy. 1 BTU is the amount of heat required to raise 1 pound of water by 1 degree Fahrenheit. BTU per hour is the benchmark used to estimate the capacity of heating systems such as gas furnaces. As to 1 ton of refrigeration capacity can freeze 1 short ton of water at 0 degrees Celsius in 24 hours. Latent heat of ice is equal to 333.55 kilojoules per kilogram. 1 short ton is equal to 2,000 pounds. Thus, 1 ton refrigeration is equal to 12,000 BTU per hour and is equal to BTU per minute and is also equal to 3.5 kilojoules per second, which is then equal to 3.5 kilowatts. 1 ton of refrigeration is the rate of the heat removal required to freeze a metric ton of water at 0 degrees Celsius in 24 hours, based on the heat of fusion being 1 ton of refrigeration is equal to 13,898 kilojoules per hour or equal to 3.861 kilowatts. As can be seen, 1 ton of refrigeration is 10% larger than 1 ton of refrigeration. Let's then tackle the few of the application of refrigeration. Applications of refrigeration in seven different industries. Refrigeration and cooling systems are designed to fulfill determined requirements based on the specific characteristics of each industries. The main industries that require refrigeration or cooling systems are district cooling, electricity production, chemical and petrochemicals, pharmaceutical, food and beverages, data centers, and other industries. Refrigeration and cooling systems are paramount for many industries to work adequately, from district cooling to data centers. Refrigeration and air conditioning. Refrigeration and air conditioning end users typically use a refrigerant in a vapor pressure cycle to cool or dehumidify a substance or space like a refrigerator cabinet, room, office building, or warehouse. Refrigerants are used in buildings for heating, ventilation, and air conditioning system to provide cooling for refrigeration and to provide cooling for industrial processes. That's all for refrigeration and thank you.